So most of you have already seen this, and the most classic example of divide and conquer is merge sort, right? Which is this O of n log n sorting algorithm. And so how does merge sort work? So let's just go over merge sort quickly. We'll do a recap of how you do the runtime analysis of merge sort, and then I'll actually tell you about a more interesting divide and conquer result. So let's just say this is an array which I'll call A to sort. So these are all, we'll just think of these as numbers, integers if you care specifically. And so how do you divide and conquer? Well, you break this array up into two parts, L and R. You sort recursively, right? So this would be the sorted version of L and the sorted version of R. And so you say, how do you do this recursively? Well, but it's recursion. So you apply it recursively, and then what you need to do is you have to combine these recursive parts into the solution for the whole. So all you need to do is to figure out this combination step, and then recursion will give you the algorithm. And so how do you do this? You have to combine these together to get the sorted version of L union R. So this is not U, but this is like, a union of everything together. And so the question is, how long does this take? How long does this merge take? So this is the merge operation. So how long does the merge take? Does anyone remember? If I give you two sorted arrays, you have to combine them into one sorted array. How long does it take? Yeah? Yeah, it's O of n, right? You have this like two pointers, right? So you have one pointer in each of them, and they'll kind of march along and sort, right? So this takes O of n time. And so it turns out there's some math you need to work, but you can combine all of this, and you get n log n. Yeah, sort of, kind of. Does this look familiar? Merge sort? Okay. So maybe, just to have this written down somewhere, I'm just going to write down like a very quick pseudocode of merge sort. I'm not going to write down the method of the merge algorithm itself. This is sort of like a classic like 101 algorithm style thing. You have these two pointers, and they just keep sort of marching down through these lists. Okay? So, and the reason that I want to sort of write out the pseudocode for merge sort is I'm more interested in how you do the runtime analysis, which creates something called a recurrence of, a time recurrence that you need to solve. Okay, so for merge sort, the first step is we'll say, if the length of A is at most 1, then just output A. This is the base case. So the second step is we do the actual splitting into two parts. So I'll say L is half of it, and R is whatever is left. And again, so this, you could take a floor or a ceiling, whatever makes sense. You could take the floor if that indexing bothers you. And then you'll say that L sort is equal to merge sort of L, R sort is merge sort of R. And finally, what we do is you output merge of, L sort and R sort. And this is a procedure that merges two sorted arrays. Yeah? And so how do you do a runtime analysis of this. And this is tricky because there are no loops. By the way, just to step back, so in some sense, the only interesting algorithmic thing that you need to figure out is how do you do the merge. And once you do the merge, then the code is basically just this, right? And so one way to think about, sometimes students get confused, like how is the sorting actually happening, is the way to think about this is really what you're doing is you're breaking the array up into lots of little parts, sorting them, and then just merging them. So all the sorting is happening in the merge, right? And it's by breaking it up into little parts and merging that overall you build the overall sorted list. So the way that you usually work this is you have to solve a recurrence, which is like in dynamic programming you had a recurrence. This is really a recurrence of the time complexity. Okay? So what I'll say is let T of n be the worst case running time of merge sort. Okay? And what I want to do is I want to figure out what T of n is. So I'm going to write a sort of equation, a functional equation in T of n, and then I solve it. Okay, so how long does the first step take? It's just O of 1. The second step, okay, it depends on whether you have pointers or copying or whatever. I'm just going to say that, let's just say it takes O of 1, because you could just use some pointers to get the array. You don't have to do a copy. What about these steps? How long do they take? Yeah? T of n over 2, right? Because, again, there's some issue with like floors and ceilings, but let's just ignore that. So T of n over 2, T of n over 2, and this final step is the O of n, right? Because there's a single loop. And so you get this, the recurrence over here, the recurrence is basically T of n is at most 2 times T of n over 2 plus O of n, right? So maybe this plus O of n, I'll say T of n is O of 1. This is the base case. This is just saying that when it's a single element, then this is just some constant time. Does this look familiar? You've seen this mostly? Yeah? Oh, and actually this should be O of n. Sorry, that was a mistake there. Yeah, okay. Right, and if you solve this, when you solve it, you get T of n is essentially O of n log n. Do you want me to solve it? Okay, all right. Let's solve it. So how do you solve it? Well, there are multiple ways. There's like you can do induction. There's something called the master theorem for recurrences that just tells you what the solution is. But what I prefer to do is do what I call the tree method, just to show you exactly what it is, because we're going to use this more heavily. So the way that you solve this is I'm going to write down the recursion tree. Right, so there's some root call which makes 2 calls, and each of these makes 2 calls, so on and so forth. Okay? What I'm going to write inside is the size of the problem being solved in that call. Okay? So here it's n, so this is n over 2, this is n over 4. Zoom in a bit. Okay, so this is the size of the input for the call. What I'm going to write next to it is I'm going to write something called the work that was done in the call. So what is the work? The work is everything other than the recursive calls. Does that make sense? So because in some sense, the recursive calls I'm kind of handling here, but this is the work done. So the work is like the runtime, but I like to call it the work. So that's the work done in that call. So I'm going to write this down here and say it's at most C times n. So C is some constant. And this is the work done in that call. So work is all the non-recursive operations. Yeah? So, good. So that is basically, if you look at the recurrence is T of n is at most 2 times T of n over 2. This is the recursive part. That's the work in the call. Right? This is the recursion. Recursive part. And this is the work done in the call. And if you prefer to look at the pseudocode, you can see that other than steps 3 and 4, 1, 2, and 5 are all O of n, totally. It's O of 1, O of 1, O of n. So it's basically O of n. Right? So ignore 3 and 4. It's basically everything. So it's like saying that to find out the total number of operations that are done, in each call, I look at what is the work done other than the recursion. Because whatever is the work done in the recursive call will be handled by those calls. Right? Another way of saying this is that in the end, if you uncoil everything, it's just a bunch of merge operations. So you're tracking all the merge operations and summing up their total time. Yeah? Don't seem very convinced. Yeah? Oh, it's a constant. So it's O of n, right? So O of n means that it's some constant times n. So you don't write O of n here because you can't. Well, okay, so this is just to be more precise. So what does this actually mean? Maybe I should write. This actually means T of n is at most 2 times T of n over 2 plus Cn for some C. Right, that's really what this means. And what this means you can really think of as this is really saying that T of 1 is at most C. Or you could assume that it's the same constant. Just pick the bigger one. Just some constant. Okay? Okay, good. So that's the amount of work done over here. So if that is the case, what is the amount of work done in this call? Yeah? Cn by 2, right? So Cn over 2, and this is at most Cn over 2. And this is going to be at most Cn over 4, Cn over 4, Cn over 4, C of n over 4. Right? And so on and so forth. So for every level of the tree, what you do is you sum up in each level. Instead of trying to sum up as you go down, you just sum up what happens at each level. Then you sum up all the levels together. Okay, so how many levels are there in the tree? Yeah, anyone? How many levels in the tree? Yeah? Log what n?
Log n.
What base?
Log base.
Log base 2. Yeah, log n, right. Of course, up to a constant, it doesn't matter. But just to be precise, we'll see that there are going to be some recurrences where knowing the exact constant is going to be important. So log base 2n, right? Because it's n over 2, n over 4, so on and so forth. Now what we'll do is, how much work is there in every level? So, yeah, exactly. So here it's at most Cn. Over here it's also at most Cn, because it's Cn by 2 plus Cn by 2. And over here it's at most Cn as well. So the amount of work that is done at every level is basically the same. Right? And that's the observation. So the amount of work done in every level is the same. There are log base 2n levels, so it's n log n. In any recurrence, I usually recommend that you write down this tree and draw it for yourself, and then it makes sense. There are formulas and theorems you can use to solve it more quickly, but this is usually when I have to solve a recurrence, I usually draw this picture, and then it just becomes clear what's going on. What you'll see is there are certain recurrences, we're going to see them, where the amount of work done in each level might actually decrease or it might increase. So in some recurrences, it'll actually decrease. In some, it'll increase. And then you have to do a little bit more math to get the final solution. So how many levels in the tree? It's n log n. So the total work in each level is at most Cn. And so the total work, which is the total runtime, over all levels, how much was that? That was Cn, which is basically O of n log n. Yeah? Okay, so hopefully this was sort of familiar, but it's useful to sort of see this again so that you have it, your memory is refreshed. Okay? And so whenever you have a divide and conquer algorithm, it looks, it's not going to look exactly like this, but it looks something like this. That you break up your problem, you do a bunch of recursive calls, then you do some extra work in putting it together. When you have that, you get a recurrence of this form, right? Where your recurrence will say T of n, the runtime at some size n is at most some number of recursive calls times the sizes of the inputs, T of the size of the inputs, plus the extra work. And T of 1 is a constant. To solve this recurrence, you have to build this sort of, you build this recursion tree, you write down the amount of work, and then you sum level by level. That's usually always the picture. You sum level by level, and then you see the pattern. Okay? Questions? Okay. So this is merge sort, which, again, most of you are familiar with. So today I want to do a more complex divide and conquer. And this is also sort of an algorithmic classic. Which is integer multiplication. Okay? So the problem is the following, which goes back to grade school. You have two numbers, x and y. And we'll just think of these as, we can do it in any base. Let's just think of normal numbers as the way we write it, base 10. Okay? And so n digits. And we'll say both of them are n digits long. Okay? And you want to multiply these numbers. This is probably, maybe not the first, but maybe the third or fourth algorithm that you learned. The first algorithm you probably learned was addition. Then you learned subtraction. And then after that, you learned multiplication, right? So I could give this to maybe, a fourth grader. I give them two numbers, ask them to multiply it, and they'll be able to multiply it for me. Maybe they'll make some mistakes, but they'll be able to multiply it. So when was the last time you did long multiplication? Not in a calculator, like actually. Yeah? Huh? 2 weeks ago. Good. So you can still do it. Why did you do it?
I forgot my calculator.
You forgot your calculator. You see? So you remember it so well that you can still do it. Okay. Good. So you did long multiplication. But presumably everyone at this point remembers how to do long multiplication. I'm hoping. Right? No? Yes? No? Okay. That's, maybe your next midterm will just have like a bunch of multiplication problems, right? First 3 problems. Okay. Now that we're computer scientists, the question is, how long does the algorithm take in terms of runtime? Okay. Oh, now everyone's like, yeah? N squared? Why n squared? Multiply each one with the other one. A little bit more detail. Yeah, it's n squared. Why? Why n squared?
When you multiply each one digit with all the...
usually you multiply, let's say you do x times y. You look at x, you multiply with the least significant digit of y, right? So basically you've broken it up into multiplying a number times one digit. And that's an O of n operation, right? Because you have to multiply, then you carry, then you do an add. But all of these things is just O of n to multiply one number with one digit. Okay? You're still not done. Then you have to add all of those things up. Well, we're not even going to divide and conquer. Why is that adding up all n squared? I mean, you're right, it's n squared, but just so that we know why. So you wrote down these numbers, right? How many numbers did you write down? And you wrote n numbers down and you do long multiplication. So you wrote down n numbers, each of which is like n digits, or maybe n plus 1 sometimes.
And then you have to make n additions?
You have to make n additions, right? Now, addition is linear time. So if you give you two n-digit numbers and ask you to add them, that's just O of n. So it's O of n, and you're doing that n times. Surprising, you never thought about long multiplication that much, did you? But you imagine, someone who's coding up like a circuit or an ALU, right, they've built in multiplication. So they write a circuit that does multiplication. And so what this tells you is that addition is O of n, but multiplication is O of n squared. Which means usually if you're building a chip, the number of gates you need to put to do multiplication is a lot more. So you have to optimize that. Right? So it's not, as we've discussed multiplying matrices and all, but in the end you have to multiply numbers. So long multiplication runs in, I should say theta of n squared. It runs exactly in n squared. Right, and just to maybe draw out a little picture, here's x, here's y. Okay, it's unfortunate that I called it x because x looks like the multiplication symbol. So I'm going to change the names. I'm going to call this capital A and capital B. Okay, much better. Okay, so what happens is usually you do A times whatever is here. You write that down here. Then you do A times the next thing. You write that down there. Put a 0 there. 0, 0. And you write down n such numbers. And then finally you start summing everything down. Right? And so that summing process, so the summing is also n squared because there are n numbers that are n digits long. Yeah?
So the actual multiplication part doesn't take any...
Well, that's also n squared, right? Because just to write down these numbers.
But like actually multiplying like for example with another number.
That you think of as like if you're multiplying two digits, that's a constant time operation. It's two digits, right? How do you do it, right? You basically have a lookup table in your head. Right? Which is what has been drilled in first grade, second grade, third grade, or maybe up to fourth grade, that you have this lookup table in your head, which is like given any two digits, you know what the result is. If you wanted to do binary, then it's even simpler, right? Because the multiplication is only with a 1 or a 0. So if it's a single bit, it's either you're just copying something down or you're doing a shift. But let's do digits because it's sort of more familiar. And so Kolmogorov, if you've seen like in general in math and computer science or in physics, the name Kolmogorov will keep coming up. So Kolmogorov was a Soviet mathematician, and in the 60s, he asked, can you do better? Right, so for like 2,000 years, people have basically been just doing long multiplication. I don't even know, maybe it's 1,000 years. Right, before you, can you imagine if you actually had written in Roman numerals, then it's not even obvious how you'd multiply an n squared. right? So the very fact that you use a place value system allows you to multiply faster. So it actually opens up this algorithm. So you do long multiplication. Kolmogorov asked, can you do better? And he thought the answer was no. So he went to a seminar and he posed this problem. So they were actually interested in building circuits. And the question they were asking was the size of the circuit. So like if you try to represent this with gates, you can do with an n-squared gate, right? Because in every gate, you could do basically and or. Addition can be broken up into ands and ors. And he thought that you could not do any better. So he had a seminar in the Soviet Union and he posed this problem. And he said that I conjecture you cannot do any better. And so there was an undergraduate student sitting in the audience, Karatsuba, and 63, he beat long multiplication. Right? And it was a shock that you could actually do something better than long multiplication. And so what we're going to do today is I'm going to show you the algorithm. How many of you have seen this? Okay, some of you have seen this. So it's basically just divide and conquer, but a very clever divide and conquer. And so I'm going to discuss the algorithm right now, but please pay attention because this is going to be your next homework, your programming homework, which is you're going to have to program this algorithm up. Except think of the numbers are huge. So instead of it being like actually an int, you have to multiply like 1,000 digit by 1,000 digit number, represented as a list. So I'll give you, you should think of it as, I actually implemented it as strings. So I have 2 strings, which are like 1,000 digits by 1,000 digits, and you have to multiply. So in my code, when I try to do 10,000 times 10,000, 10,000 digit number times 10,000, my code essentially, I don't know, I just gave up after 10 minutes. But with Karatsuba, I could do it in a few minutes. Could actually multiply the numbers. Okay. So what I'm going to do is I'm going to show you how to do this by divide and conquer. I'm going to show you the wrong way of doing it. And you'll see that the wrong way basically just gives you long multiplication again. And then there's a clever trick, and the trick will lead to the improvement. So if you wanted to do divide and conquer, so this is A, and this is B. And so we want to do this multiply AB. So I'm going to do it by recursion as following. So what would you do? You'd say, okay, let's divide this into 2 parts. So you just take the digits, right? The first part, the second part, and I'll call this A high and A low, B high and B low. Right? So essentially A is equal to 10 to the n over 2 A high plus A low. B is equal to 10 to the n over 2 B high plus B low. Right? I've just broken up the digits. Okay. So this makes sense. So I broke this up. This here. So if I just write out, basically using algebra, what A times B is, I'll get 10 to the n, A high, B high, plus 10 to the n over 2, A low, B high, plus A high, B low, plus A low times B low. Yeah? Oh, so I'm just saying that this is an n-digit number. So what is it? If I want to represent A in terms of AH as a number, then like this number is really just an n over 2 digit number. So it's like shifting it by that many zeros and adding the next. Does that make sense? Yeah, question?
Yeah, I was just going to ask the same.
Okay.
How did you get A equals?
I mean, okay, so maybe I should just write an example. So suppose A was 2597. Then all I'm saying is that A high is equal to 25 and A low is equal to 97. And then I'm just saying that A is really 10 to the 4 over 2 because it's 4 digits, right? So it's 10 squared times 25 plus 97. Does that clear it up? Okay, so sorry. So it's just saying that you're just taking like the top half, you're shifting it, and then you're adding the next thing, right? The reason I'm doing this is because I want to kind of break up the multiplication of A and B into smaller multiplications, but probably more of them. Okay? Yeah, so far so good? Okay. So then I could write this, right? And these are all multiplications of n over 2 digit numbers. Yeah? So how many multiplications are you then doing of the smaller version? How many smaller multiplications are you doing? How many do you need to do? Three? Why 3? 4. Right? Because you have to multiply this, you have to multiply this, this, and this. Yeah? This thing. So it's 10 to the n over 2 AH plus AL. That's what A is. Times 10 to the n over 2 BH plus BL. Then just expand it out. It's going to be this thing times this thing times this thing, this times this. Right? Just open up the parentheses. All just, middle school math here. That's all we're going to do here today. Middle school math. And then we're going to end up with this result. Yeah?
We just count the multiplication by tens as...
Yeah, you can just, okay, sorry, I should have, you could just do, multiplication by 10 is just a shift, right? So you, like, in terms of runtime, it costs you just linear. So maybe you're right, so that's a good point. So suppose I'll write this out now, but if I'm writing a recursive procedure, and I basically compute AH, BH using the recursive procedure, then I can just append it with n zeros, and that's just a linear time operation. So multiplying by 10 is simple. Yeah, good point, yeah. So this is a shift. And that's also a shift operation. Which is, again, going back to how you think about it, right? Multiplying by 10 is not something that you need to memorize or do. Or actually, that sort of involves any computation beyond just shifting. But it's the other operations that require some kind of computation. So let me write this out sort of more precisely. Okay, so there could be, say, minor off by ones in what I'm writing. I don't want to get into the exact indexing, otherwise the code becomes too long to write. But just think of it as roughly, when I multiply two n-digit numbers, I'm going to get something, it could either be 2n digits or 2n plus 1. I'm not going to worry about whether it's plus 1 or not. So I just want to write down a simple description so that we can discuss what is the running time of this different way of doing multiplication. Now you can imagine doing this recursively. Right? And now it's not so clear what the runtime is anymore. Or I don't know, maybe it is for you. But it certainly isn't for me. Right? So you see that you could basically write the code in the following way. So actually I'll write multiply A, B. I'm just going to assume both of them have the same number of digits. Okay? But the code can be modified to do both. So I'll say if the length of A is, let's say, less than 1, so at most 1, then just return the answer by long multiplication. Right? So one of them is a one-digit number, just do long multiplication. It's fine. This is your base case now. Then we'll say, A, H. Thinking of this like as a list. Over 2, A low is n over 2 plus 1 to n minus 1. B low is n over 2 plus 1 to n minus 1. Right? So this is just splitting the way that you split for merge sort. Now, just using recursion, I'll do multiply AH, BH, multiply AH, BL, multiply AL, BH, multiply AL, BL. Because these were all the products that you needed. So I'm just going to recursively multiply them. Again, to save myself a little bit of work in writing and not coming up with variables, I'm not going to store all of these in variables. I'm just going to say that's AHBH. Now you know what it is. And so then compute 10 to the n AH, BH by shifting by n places. Right? So this means that once you have AH, BH, you can just shift it, and then you have AH, BH times n. Compute AL, BH plus AH, BL by addition. This is again something you know how to do in linear time. So all linear time steps I'm kind of treating as the merge. Then you can compute 10 to the n over 2 AL BH by shifting again. And then finally you return 10 to the n AH BH plus 10 to the n over 2 AL BH AH BL plus AL BL. Right, this is an addition. Yeah?
Where's the multiplication?
Huh?
Which step do we multiply?
There is no multiplication. It's divide and conquer. Just like in sorting, merge sort, you can say, where did the sorting happen? When you say, where did the multiplication happen, even in long multiplication, where were you actually multiplying? One digit. Suppose it was binary. So if you really wanted to know where did the actual multiplication of any digit happened, that would be your base case. Right? So in your base case, when you have two one-digit numbers, you're going to multiply them. But if you did binary, there's it's all just shifting. Yeah.
We also need a base case of length of b is less than or equal to 1.
Yeah. So I'm assuming both the lengths are the same.
Okay.
Just to keep it simple, that's what n means over here. So assume lengths are the same. But you could do this, or length of b is less than 1. Don't you worry, you're going to code this up for your next assignment. So all of this is going to be crystal clear once you write the code and deal with all the errors. Okay? Yeah?
Step 7, that's 10 to the n over 2.
No, it should be 10 to the n. Because the 10 to the n over 2 times n over 2 is 10 to the n. Yeah, thanks. Yeah. Okay? So, new way of multiplication. Right? Maybe this is what I should do in the midterm, right? Basically write down two long numbers and say multiply it using this other method and show me the steps. Okay? So this is, you're just doing divide and conquer. Okay. So now let's write down the runtime. So this is just O of 1. And as we argued, this is just O of 1. Now each of these operations is T n over 2. Okay? And all of these steps, these are just O of n. Yeah?
What's T?
So T of n is the running time, I should say worst case running time of multiply. Right? I'm trying to figure out what the running time is. So I'm assuming, just like I did for merge sort, right? What I did for merge sort is I said T of n is the worst case runtime of merge sort, and then try to break up the runtime in this way. I'm doing the exact same thing for this long multiplication. Or not this long, this recursive multiplication. I'm following the exact same paradigm, which is the divide and conquer setup. Yeah? Questions? So far so good? Okay? Okay. Given that that is the case, what is my recurrence now? Yeah? 4 times T n over 2 plus an O of n. Right? And then T of 1. So this is going to be at most some constant, and this is some constant times n. So this is just some constant. Right? This is what you get. What this says is, you break up one multiplication into 4 multiplications of half the size, and then you do linear amount of work to put them together. This is my recurrence now. The question is, maybe this recurrence is going to beat n squared, and then you're already done. You have a faster way of multiplying. Right? So, how do we solve this recurrence? We'll again just build out the tree, and we'll see what happens. Yeah, questions? So far so good? It's pretty straightforward at this point. Okay. Okay, so let's write down the tree again. So this was n. But unlike merge sort, it makes 4 calls. N over 2. This is n over 4. And the amount of work done is at most Cn over 2. So on and so forth. Okay? So how many levels in the tree? Yeah? How many levels in the tree? Good. How many levels in the tree? Yeah, how many levels in this tree? Log base 4 of n. Okay. One option. What else? It's just log base 2 of n. Why? The size of the problem is only dividing by 2. It's the branching which is 4. But the number of levels in the tree is still log base 2 of n. Right? Because n over 2, n over 4, n over 8. It's just more calls in each level. But the number of levels in the tree is exactly the same. Right? So log base 2 of n levels. Right? How many calls at each level? Okay, now I'm going to force you to answer. Yeah, tell me now. How many calls at each level? So I is the level. Right? So I is the level. Okay, I is the level. How many calls at each level? I'll give you a minute to sort of Yeah, question?
Is the top level 0 or 1?
Good question. Top level is 0. Yeah, how many? What is it? 4, 4. It's 4 to the I, right? So the difference with merge sort is the number of calls actually is just 2 to the I. But here it's 4 to the I. Right? So it's basically squaring. What is the total work in each level? Okay, so again, let's do the ith level. What is the work? Okay, is the work going to be Cn times 2 to the I? Is it Cn times 4 to the I? Or is it just Cn, like at most? What is the best bound? The total work at each level, right? So what am I doing? I'm summing up in each level. You'll probably have to write to figure this out. How much is the work done at each level? Yeah, I'll give you a minute to ponder. Like it's a little hard to just guess off the top of your head. Yeah, question. N is the total size of the input. Yeah, N is the size of the input. So clearly you can see that the first level it's Cn at most. Yeah, so what's the answer now? And now it's all over the place. Everyone's guessing a different answer. Yeah, what someone said something, yeah? What was your guess? Yeah. Why? Okay. Okay. Good. So you just did the calculation for the first two and guessed the thing that matches, which is correct. But now mathematically give me why it should hold for any level I. Why is it? This is right. This is right. But why? So you did it out for the first few levels, yeah?
Yeah, so it's like 4 to the I calls at each level.
Yep.
And then at each level, the amount of work per call howls. So it's 2 to the I.
You're dividing by 2 to the I.
Yeah.
Exactly. So the number of calls at each level is 4 to the I, right? But what is the work done in a call at level I? At every level, the work is halving. So that work is Cn divided by 2 to the I. And so you put this together, you get 2 to the I times Cn, or Cn times 2 to the I. Yeah?
Can you remind me why is it Cn for the first level?
So think of this as Cn is just some additional constant work that you do at every level. So if you go back to this code, right? You go back to this code, what is that work? It's basically all of this stuff. All of the time spent in that addition. So the point is the time spent in the addition is linear in the size at that level.
But it's just adding 3 numbers.
There are 3 numbers that are n digits long.
And adding 3 numbers in n digits long is O(n).
How long? You tell me, right? Now, if I give you 2 numbers that are 100 digits long, and I ask you to add them, how many additions, individual additions do you need to do? You need to do like 100, maybe if you have carries, you might have to do 200. It's linear in the size, right? Don't think of these as ints. Don't think of it as an int, you'll get confused. It's like a long list. It's not like you store this in an int. You cannot store. What is the largest integer you could store in an int? How many bits? 64 if you're doing, depending if it's a long, it's 64. Typically it's 32, but a long would be 64. What if I gave you like 1,000-bit number? Right? Do people compute additions that long? Well, in cryptography, they will use digits that are like 256 bits, right? Which you cannot store in a long. Okay? Yeah.
So back to the summing part of the.
So by the way, is this clear? So this addition is linear in the size of the input, right? Yeah. Okay. So now tell me, yes.
So the summing part, the
You mean, sorry, integer, you mean this part here, long multiplication?
Yeah, the long multiplication.
Yeah, that summing part is n squared.
Okay.
Because you have n digit numbers. Yeah? So here you have like whatever, 4 n digit numbers. Yeah? Okay, good. So, yeah, does this make sense now? So this is the amount of work that is done at every level. So there are like these 3 or 4 additions you need to do, and the sizes of the things are n divided by 2 to the I, so you multiply them, you get 2 to the ICN. Okay? So this, if you think about it, the total work at each level is increasing exponentially. Okay? It is not like merge sort. In merge sort, the total amount of work was essentially the same at every level. But now it's actually increasing exponentially. So it's a different kind of recurrence. Yeah? Okay? So now to get the total runtime, we have to sum up the total work at all the levels. Okay? So now it's like, now your next discrete math question. So the total work the total running time, I mean, technically it's at most, but I have the levels going from 0 up to log base 2 of n of C of n times 2 to the I. So in merge sort, there was no 2 to the I, so it was Cn log n. So now you have this Cn, I is equal to 0, log base 2 of n, 2 to the I. What is this number? Right? You need to work it out. So, up to constants, right? I don't care about the constants. Is this thing basically just n? Up to constants again. Up to constant factors. Meaning, I don't care if it's, when I mean n, it could be maybe n plus 1, or maybe it's like 2 times n, 4 times n, I don't care. Is it n squared? Or is it just log base 2n? This question makes sense? This summation over here, up to constant factors, which of these is it? Or actually, no, sorry. Is it n log n? Sorry. Is it n, is it n squared, or is it n log n? Yeah? What's there in that square? What's there in the square? Not the whole thing. Good. The thing in the square. It's some geometric series, right? 1 plus 2 plus 2 squared plus 2 cubed, so on and so forth. So how much is it? Yeah. All those vestiges of discrete math knowledge which you buried in your head, or maybe like tried to purge as soon as the exam was over. Now it comes flooding back. How much is it? Yeah, okay, so why? Yeah?
So at the last step, you're going to have 2 to the power of log 2 of n.
Yes.
That's going to simplify to n.
But what about all the other steps before?
Those are constants now.
No, it's n. The previous one was n over 2. One before that was n over 4. Right? So you got the right answer with the wrong reasoning. Yeah?
We can sort of imagine it backwards, where like the last one is like 1, and then you have half, and then you have quarter, and then sums to 2.
Yeah. It's a geometric series, right? So it's like, basically, what is this? It's n plus n over 2 plus n over 4 plus n over 8, so on and so forth, which you can also write as n1 plus half plus 1/4 plus 1/8, so on and so forth. And this thing is at most 2. It's a geometric series that converges. In general, when you have a geometric series, the sum is dominated by the largest term, right? Which the human societies saw most dramatically during COVID, which is that the number of people who overwhelmed the hospital are the people who basically got COVID the last day, right? Because it's an exponentially growing curve. That's why hospitals were getting overwhelmed, because the number of people who would catch it at the very next day would be much more than what happened before, or would be a large fraction of that. So basically you get n, and the total runtime over here is just O of n squared all over again. So we did all this hard work. I made you go through all these calculations, forced you to do all of this, just to give you a method that ends up being long multiplication all over again. Yeah?
So going back to the previous page.
Yep.
But did we say it's n?
The thing in the box is n, but you're multiplying by c times n.
Oh, gotcha.
Yeah, right? So the thing in the, you're right, so just to, yeah, good. Thanks for pointing. The thing in the box is n, but it's cn times n, so it's just n squared. So you do this like fancy divide and conquer, and you don't beat the grade school kid anymore, right? You just did it in a more complicated. It probably is even worse because there are more constant factors overhead. Okay? All right, so but this is where Karatsuba started. So okay, so it's 9 o'clock, so let me take a break for a few minutes. Okay, and then when we come back, I'll show you Karatsuba's solution. Okay, so let's get back to Karatsuba's multiplication. Let's see. So I'm going to go back to this equation over here. So if you remember, let me get this. Why did we need 4 multiplications? Because we had to compute 4 products. Like suppose if we could do it with 2 products, then it would actually just give you merge sort all over again. Like suppose magically you could just actually figure out 2 things to multiply. Then you would get T of n is less than 2 T n over 2 plus O of n, and then you'd get n log n. So the fact that it's 4 multiplications really makes it n squared. And the question is whether you can cut down the number of multiplications. But it doesn't, it seems like, but fundamentally there are 4 products that you're computing. So the Karatsuba trick was this sort of remarkable observation that he had. He said, okay, suppose you do the following. Now, this is going to be a very strange multiplication, but you did, so recall, just to get all the pictures in one place. Right? So this is what we had, right? So AL, so when you're doing multiplication, you're basically doing like this cross multiplication, which makes sense. So he said actually, if you add AH plus AL times BH plus BL. So it's very strange. What he said is take the first half, add it to the second half in the same number, which is not something that you would ever do when you're multiplying. Like, why should you do that? But he said if you look at this product, you get AH BH plus AL BH plus AH BL plus AL BL. Does that make sense? And he said these 2 things you've already computed. Right? Because this is what you did anyway over here. So maybe I'll move all of this in one place. So you want these 4 things, but technically you only need 3 of them. You only need the sum of these. You don't need to know each of them individually. So what he said is if you take AH plus AL and BH plus BL and you multiply that, you actually get what you want, but you get this additional stuff. But this you're going to compute anyway for these, so just subtract them out. Okay? Yeah?
That would be 3 multiplications.
Yes. But more additions. You have to do more additions, but it turns out that the addition only affects the constant factor. So you can actually do the seemingly, instead of doing 4 multiplications, you only need these 3 terms, and he had this sort of way of figuring out what that 3rd term is by doing additions and subtractions.
And if you just find one of the AH, BH, and AL, BL, and never mind.
Okay? So I have no idea how he observed this. Right? Because this is a very strange, it's a very counterintuitive thing to do, which is to actually get this term over here, you're actually going to use subtraction. Which if you think about it, like in long multiplication, you never subtract, you only add. And even in the recursive thing, you only add. But what he said is you can do subtractions instead. But the running time of subtraction is the same as addition. It's just O of n, right? It's again the same formula that you have for addition, except you have a borrow instead of a carry. Anyway, you're going to have to code all of this up. So all of that stuff will be painfully clear to you soon enough. Okay, good. So you have this. And so essentially his identity is to say, I'm just writing this out separately, AHBL, which is again this term that we wanted here, ALBH plus AHBL which you can think of as sort of the cross term. Like one is AHBH, multiply the high parts, multiply the low parts. Then the cross you multiply and then add. So you don't need to know each of them individually. That's what saves you the work. You don't need to know what AH times BL is. You only need to know the sum of those two things. And so this, he said, was that minus AHBH minus ALBL. And so he says you do this multiplication, you do this multiplication, you do this multiplication. So you do 3 multiplications, and then you do a bunch of subtractions to get what you want, and then you put it all together. Okay? So I'll write this out over here. So I'm not going to write out the base case and all of those things. I leave it to you when you're going to write the code to figure that out. What he basically said was one way of doing this is, so you first compute what I'll call C, which is AL plus AH, and D, which is BH plus BL. Then you recursively compute C times D, that's one product. You do AH, BH, and AL, BL. Then you basically you add, you do 10 to the n AH, BH plus 10 to the n over 2 CD minus AH, BH minus AL, BL plus AL, BL. Does this make sense? Right? So you basically, you got that middle part. Instead of doing 2 multiplications for it, you just did 1 multiplication, but there's some extra work in terms of the additions. But that addition, that's just like an O of n term. So you'll see that if we now write down the recurrence over here, so if T of n is the runtime, so if T of n is the worst case running time, so the worst case runtime. So remember that before we had this recurrence of T of n is at most 4 times T of n over 2 plus Cn. Now we're going to get 3 times T of n over 2 plus, I put C prime, maybe it's some larger constant, but it's still some constant. And again, T of 1, no C prime, and this is just some constant. Question? Okay? So the difference between these recurrences, so technically, to be really precise, there are 2 differences. One is it becomes 3 as opposed to 4, and the constant is different. But the constant you'll see is just something in the big O. It doesn't really affect the asymptotic runtime. So the question is, what is the solution of this recurrence? Are we going to get something better than n squared? We will. So we're going to get something that is better than n squared, but it's going to be worse than n log n, because n log n would mean 2Tn over 2. Okay? So let's just go ahead and do the tree. I mean, again, we can write down the formula, but I think it's, if you see the tree, you'll see where the savings come from. So it's n over 2. N over 4. So on and so forth. And again, the work is again this linear. So, some C prime n, C prime n over 2, C prime n over 4, so on and so forth. Okay? So, at the ith level, how many calls? Is it 2 to the I, 3 to the I, or 4 to the I? It's probably relatively easy to see. It's 3 to the I. So in this case, it was 4 to the I. And now it's become 3 to the I. So that is your savings. So the total work at each level now becomes this sort of, so I'll write this down here. So this is, you get O of n over here. So, or whatever, you get C prime n. Now what you get is you get C prime n times 3 over 2, because there are 3 calls. What do you get over here? 9 over 4, which is, in terms of 3 over 2, what is that? 3 over 2 squared. Right? So you get 3 over 2 squared. Because the number of calls is going as 3 to the I, but the work per call is going down as 2 to the I. So you multiply them together, and so the total work at each level is essentially some constant times 3 over 2 to the power I. Again, I put a different constant than the other one just to emphasize that this constant is different from what you had from the previous multiplication method. But it's just a constant. So it's also increasing exponentially. Right? But it's increasing exponentially with a lower rate. Okay, so in the simple recursive multiplication, it was increasing as 2 to the I. Now it's increasing as 1.5 to the I. Okay? And the thing is, in the long term, if you have a smaller base, or whatever, if that base is smaller, then the wins basically become large as you go further along. So now what is the total amount of work? So this is a little bit of math to be done, the total running time. So anyway, so I should pause. Any questions at this point? Is this clear? Just to sort of recap over here, remember that the multiplication has to be done in this way. So when you write the code, at this point it's probably worth mentioning, because I'm going to ask you to code this thing up. AH, BH, A, B, all of these things are lists that are long. I implemented it as a string, just because it was convenient to think of it as inputting a string. So the string is like a string of digits, and the output is a string of digits. And so in the string, you're now going to have to code up how do you add 2 strings? How do you subtract 2 strings? So you have to literally write code for like the process of addition, the process of subtraction, and then the process of shifting, which is you take a string and then you just append zeros to it. You can do it to the list. Anything is fine. Okay? And then you could write this code up then. Does this sort of make sense? Of course, your code will have to deal with the case when the inputs might not have the same length, but all of those are mostly just, once you get the basic idea, it's not too difficult to do. Okay? Questions? Okay, good. So now what is the total running time going to come to? So I'll just say, it's up to constants, right? So it's like, okay, so it's I going from 0. It's again log base 2n, because the calls are still halving at each level. It's n over 2, n over 4, so on and so forth. The number of levels is still log base 2n. But it's 3 over 2 to the I times some constant. So it's just writing it out over here. Okay. Now again, as we said, this is a geometric series. So up to a constant factor, the sum is just dominated by the last term. So you just look at the last term, and then the exact term is, it depends on what this constant is. So I'm just going to write this with big O. So this is O of n times whatever that last term is, which is 3 over 2 to the power log base 2n. Right? That was what the last term is. That's what the sum is. And so you get O of n times 3 log base 2n divided by 2 log base 2n. Okay? Now, these are just the same thing. So what you get is, I wish I could have written this in one page, but anyway. So you get that the total runtime is O of 3 to the log base 2n, which is, if you do some manipulations with the logs, you can write this as 2 log base 2 3 times log base 2n. What you get is this O of n to the log base 2 of 3. And so log base 2 of 3 is between 1 and 2, right? It's something in between. And if you write it out, it's like n to the 1.58 something. So it's some constant, which is between 2 and 3. It's sort of like n to the 1.5, but a little bit more than that. Okay? So will you see the differences of this runtime when you write code? And the answer is you have to make your n a little bit large, because the constants in this are worse. So what you'll do for your homework is you're going to code up long multiplication, okay, as a benchmark or a baseline, and then you're going to write code for Karatsuba. And then you're going to do like many runs of it and plot the runtimes. And you will see the runtimes will start diverging. Even at about, I think, in my code, at about 1,000 digits, Karatsuba was about 4 times faster. And then it just kept increasing. Okay? So what you have is you can multiply in n to the 1.58. So just to give you some context, like just rough guesses, suppose your n was 1,000,000. Although I'm not going to make you do 1,000,000. If you do long multiplication, that's like 10 to the 12 operations. Infeasible, right? That's basically a quadrillion operations. If you do Karatsuba, you're kind of like, it's about 10 to the 9, 10 to the 10, which is actually feasible. So if you had to multiply something that is that long, although I don't think there are any applications these days that need to multiply things that are that long, but still, just as to understand multiplication, see, for the first time in, I guess, like 2,000 years, someone came and actually improved on how to multiply 2 integers. And the solution is just divide and conquer. The problem, of course, with divide and conquer is like, how do you come up with this trick? Right? And that's, I don't know, that's very difficult. Yeah?
Was this proven at some point, like mathematically?
Yeah.
That's actually
Which, this?
yeah, no, like how you said. Well, yeah, I guess
This is the proof. I just showed you the proof, yeah. But yes, there is a research, there's a paper that he wrote in 1963, but this is the paper. Like at this point, you know the proof. Yeah?
I guess like in general, is this like a field of research to see if you can like improve this even more?
Yep. I will yeah, I have a series of things to, yes, I will tell you right now. So the question, of course, is, this seems like such a fundamental question, right? How long does it take to multiply 2 integers? And what is the fastest algorithm out there? So as soon as this came out, there was a result by Toom and Cook. What they did was essentially they said, well, instead of breaking it up into 2 parts, you try to break it up into 3 parts and do something less than 9 multiplications. Right? And you kind of build on this, and then they got some improvements on this. But it didn't go that far until Schoenhager and Strassen in 1971 got it down almost to, I mean, it's this funny log n thing at the end, but they got almost n log n, and they used something called the fast Fourier transform. They used the fast Fourier transform, and they got it down, which, again, this is an algorithm that can be shown in this class. Like, it would take one lecture, but what is kind of crazy, it requires complex numbers. So actually, just to multiply two integers, you're going to do some arithmetic on complex numbers and matrices and linear algebra, and then bring it back down to integers. And you can do it in n log n log log n. And for the longest time, it was not clear whether you could improve on that, until there was actually Führer. This was in 2007. So we're getting much closer to. I mean, the question was really, do you need this log log n? Can you just get it to n log n? He got something called 2 to the log star n, which, ignore what that is, but that's something even smaller. So at this point, this algorithm is practical. But beyond that, they're less practical. And then the latest is there's Harvey and van der Hoeven this is 2019, so this is not that long ago, where they actually got it down to n log n. And this is like a 60-page math paper. It's like a long thing, but they actually gave an n log n algorithm to multiply two integers. And as far as I think you cannot beat n log n, though I'm not sure. Yeah?
You know those algorithms are implemented like in processors?
These, no. The fast Fourier transform is very implementable. So I don't know if they actually use the fast Fourier transform in building circuits, but it is used for many other things, where the fast Fourier transform is implemented. Specifically, like, do they use this in building circuits? Maybe they do the FFT. I'm not sure, though. But the others, no. I mean, the others. I mean, the constant factors are really bad. So at some point, if you're really looking at building something, then the constant factors matter. So the constant factor here is 10 times more than that, or 10 times more than long multiplication. It might only be worthwhile when n is sufficiently large. You will see that even when you do Karatsuba versus long multiplication, is that when n is small, maybe up to a few hundreds, long multiplication might just be faster, because the constant factor for long multiplication is smaller. Because Karatsuba is going to do all these like weird subtractions and additions, and that kind of starts adding up. No pun intended. So when n is, once it crosses some point, then it becomes better. So if you wanted to know whether to implement this or not, you have to do a more careful analysis and see where the crossover point is. But again, the fast Fourier transform as an algorithm is implemented for other signal processing tasks. Yeah. This one? This one I have no idea. I don't know. I've looked at the paper, but I haven't read through it. Like, it probably is. The issue is that a lot of these things, they will do arithmetic over like some weird algebra. So you have to first basically write code for that algebra and then do the implementation there. So it could be maybe, I don't know. Like, even the FFT, my guess would be like maybe 400 lines of code. Yeah, I don't know. Maybe it's less than that. But the whole point is, like, you're doing something very strange here, which is you're going to take complex numbers. You're going to take like the nth root of unity, which is like some weird, some irrational number, and you're going to have to start playing around with that. So you have to basically write code to implement additions and subtractions of complex numbers, and then deal with that. Yeah. Yeah?
Out of curiosity, what's log star?
Log star? Yeah. So log star is the number of logs to take to bring it down to 1. So it's like saying that, like, you could keep doing, it's called the iterated log. So you take n, you do a log, then you do a log again, you do a log again, and you say, how many times do you need to do before this becomes, let's say, less than 2, less than a constant? In practice, this is like, for n, like billions, this is like 4. It's a very slowly growing function. Even log n is practically like, 3 or 4 for any practical application that you have to worry about. But the fast Fourier transform is used for actually like multiplying, if you want to multiply two polynomials. A lot of this is related to multiplying polynomials. You think about how do you multiply polynomials from middle school, you basically take each term and you keep cross multiplying. Right? And so